Morning, everybody. Welcome to the UKBIC webinar. With me today, I have my colleagues Helen Walker and I have Kenneth with me. Just a couple of things before we start, so everybody's aware of how to be in touch with us. At the end, we will have a session for questions and answers. If you could kindly put the Q&A function on Teams as opposed to the chat, and that's much better for us to make sure we get through those questions. We'll get through as many as we can. Any that we don't, if you wanted to contact UKBIC after the webinar, if it's a sales inquiry, could you email sales@ukbic.co.uk, or you can send general inquiry to info@ukbic.co.uk. However, if you're a potential supplier, if you could use suppliers@ukbic.co.uk, that will be very helpful to us. Copy of the slides and recording of the presentation will be available via UKBIC's website from 14th of April 2025. The webinar today is about exploring UKBIC's electrochemical and process simulation capabilities, which is the latest one in our series of webinars. The way we'll run it is I will do a small introduction for UKBIC. Apologies to those who are regulars to our webinars. This is for the people who don't, just a brief introduction about UKBIC capabilities, what we can offer, and then we will get into Helen and Kenneth. So UKBIC was set up to address the issue of the UK battery ecosystem. It was found to be somewhat lacking. So Faraday Battery Challenge was set up by the government, and it sits on three pillars: research, development, and then upscale. UKBIC is part of the upscale side of it. Our role is essentially to help people scale their business to industrial levels. Where we sit within that ecosystem is the early scale, which is the Faraday side, is your TRL 1 and 2. Then the more advanced organizations working at kilogram scale are your more technical universities. Then UKBIC came in originally around TRL 7, TRL 8, where we're at the thousands of kilograms, which is the precursor to gigafactories. However, we realized there was a small gap within that market, and we're now addressing that with the tens of kilogram scale with our flexible pilot line and some of our newer capabilities that we have at UKBIC. So our role here is to help de-risk investment and upscaling of manufacturing. Quite often you have people that have a refined chemistry and they have customers. Then they have investors who want to invest. However, the customer wants to see the product at volume. The investor wants to see the product manufactured at volume. And that's where we will sit in. We will help people get to that point where we can run product at industrial scale ready for gigafactory manufacture. We have here standard line, 2 lines. You will see this in any gigafactory where we have electrode for anode and cathode. Then we will have our cell assembly where we're making either 21,700 cylinders or 300 by 100 pouch. From there, we'll have formation age test, and the cells and pouches that come out of there will either go into module and pack, or they will go to customers. Our whole role here is to help people get a product to market, is to help people industrialize what they do. One of the key features around working with UKBIC is that we're not interested in your IP. You may have your background IP. Any IP we develop with you will be wrapped up at the end, and that then makes you successful in terms of your business. For us, we cover most sectors that people are aware of. We are not purely automotive. We do cover extensive market sectors, as you can see. So from here on in, I will now introduce our resident simulation experts that we have here at UKBIC, and they will explore the UKBIC's electrochemical and process simulation capabilities. Over to Ken.
Thank you, Rob. So in a continuation with the presentation, I will go through my slides that will be discussing about product simulation at UKBIC and then process simulation at UKBIC. So at UKBIC, we are heavily involved in simulation and modeling to support the production and cell fabrication processes that goes on here. The simulation activities are divided into two categories. So we have the product simulation, and that's heavily involves performing design and optimization and performance predictions of our products. So our products can range from cells of different formats, that's cylindrical, pouch, and prismatic cells of different sizes. And when they are also assembled into module and pack. In addition to that, we also do the process simulation that involves modeling the processes involved in cell manufacturing. So that includes mixing, slowly coating and drying. And this processes heavily uses physics-based model and data-driven modeling techniques. So my name is Kenneth Nwanoro, and I'll go through the electrochemical modeling processes. And after, I'll hand over to my colleague Helen, and she's going to take us through the process simulation slides. So at UKBIC, our core business is cell, module, and pack. So to be able to design those, produce them, that they will meet the target performance, we use simulation to do that. So at cell design level, we design the cells, and then we go through simulation processes where we predict the voltage profiles, the performance metrics of that. So this includes checking for different cycle protocols, checking for charge and discharge protocols, determine if there are going to be some lithium plating, if the cell is going to meet the design performance. So the plots that you see there are some of the simulations that we perform even before the cells are built. So this shows you that we have the capability to design, model, and then build cells with high accuracy. In the next slide, I am going to talk about the cell and battery life prediction that we do here at UKBIC. Cell cycling is quite very time-consuming and expensive. So here we've developed some highly accurate models that captures some of the degradation mechanics in lithium-ion battery cells and battery modules and pack. And here we can model different degradation processes that includes SCI growth, lithium plating, all these side reactions that happens in the cell that results into power fade and capacity fade. We have the capability to model that, and we can do these simulations under multiple operating conditions. So we can look at multiple drive cycles at different temperatures. We can look at particle cracking and electrocracking. This involves coupling mechanical stresses into our model. What we can predict can range from predicting the cell cycle life even before they are manufactured, even before you do the first mix. We can tell you how long these cells are going to last if you cycle them under these set conditions. So we can also, once we start cycling the cells, once the cells are built, we can predict the remaining useful life, and we can tell you the power and capacity fade, and also predict some of the changes in the cell electrochemical behavior. So this capability is based on the fact that we have the tools to be able to predict this, and also the capability to build this high accurate model. So the plot that you see there is the orange one, or the prediction, is the cycle life that we predicted for our Mark II standard pouch cell. And the blue one is the actual test data that we got when we actually produced the cell. And as you can see that the model accuracy is quite very high. You will also notice that there are some kind of spikes, and that is because when the cells were actually tested, we had some checkups, like every 50 cycles, And that doesn't mean that the prediction accuracy is wrong. As you can see that after that checkup test, the test data actually did correspond with the prediction. In addition to cell performance modeling and cycle life prediction, building cell is quite challenging, designing is quite challenging because you want to gain power, you want to gain energy, you want to reduce costs, you want to increase life cycle, and at the same time, you want the cell to be safe. So achieving a balance between these metrics is quite challenging. So here at UKBIC, we developed some highly accurate and sophisticated optimization algorithms that helps you to do cell design, module and part design optimization, which means that you can optimize the performance that you want just purely from simulation. You can gain some sensitivity intelligence from performing these simulations. There are some insights that you can gain through our multi-objective optimization algorithm that we developed here. And through this process as well, you can gain a lot of different design options very quick. So you have the capability to generate thousands of different design options. So the images that you see on that slide is our Mark II tablets that is coming up. I mean, it's a challenge to achieve a market-leading capacity cell, high energy cell, while at the same time being able to fit them inside the can. So this is a 21700 cell. So by using these multi-objective optimization approaches that we develop here and the capability that we have, we've been able to manage to achieve the target capacity and also ensure that the cell is actually going to fit in the intended assembly can. So these are some of the capabilities that we have here at UKBIC that we've developed. We use these capabilities to help our cell design processes, and also this capability can be developed into a ready-made tool that is ready to be used by the customer if they want. So I've talked about the performance simulation, the design optimization that we do here at UKBIC. Now I'll go into the modeling approaches that we use. Our modeling is a multi-scale and multi-domain model. Multi-scale, what I mean there is that our model can range by, we can model a cell by just a single particle, or even using the famous P2D model. And again, that does not also mean that our model cannot increase or extend to a much larger scale. So at P2D level or single particle level, we use that for cell design optimization. So you've seen the design optimization. You can run a huge microstructure model just to design the cell. So we use these single particle models and the DFN models to do this. But again, you also want to see some of the macroscopic performance of the cell, such as you want to look at the temperature distribution in the can, in the coil pack assembly, in the jelly roll, or even a power cell. You want to look at some of the macroscopic performance, and that is where our model landscape can increase, where we use PXD models. So PXD model, I mean, you have like P2D, P3D, and P4D models. Again, sometimes we want to understand some of the bottlenecks in the species transport or effective transport properties of a cell. Say we want to optimize the particle sizes, we want to increase the tortuosity or get the optimal porosity, then we dive deep into a resolved mesoscale microstructure model. And we have all the capabilities to do this at UKBIC. Our model is also quite multi-physics in nature, so all I've been talking about so far is electrochemical, but again, we can couple that with thermal, mechanical, and even cooling strategies involving CFDs. Again, we are quite versatile when it comes to chemistries and materials. Our simulations can cater for lithium-ion battery, sodium-ion batteries, and even any other emerging chemistries that are out there. So, in addition to these capabilities, you can see that our simulations are quite very accurate, and you start wondering, how is it so accurate? And that is because we have the capabilities to do a detailed and highly accurate model parameterization capabilities. This capability comes from the fact that we have the in-depth knowledge of the model that we implement in developing this design of simulation processes. And that is because we have these multi-objective optimization tools, and we have one of the best labs in the world where we can do a full cell teardown, perform some of the measurements that we need to be able to extract the required parameters, which we can then test in our model and see how accurate they are. And then these models can then be developed and they're ready to be deployed to be used for cell performance analysis and cell design analysis. As you can see, some of the plots that I showed there, these are that is the temperature prediction or the cell temperature response that we predicted even before the cell was built here at UKBIC. And then once you got the pilot line data, we match that and we see how accurate they are. And in the middle plot there, you can see is the cycle life data that we predicted for 1,000 cycles, and then we got data from our pilot line. You can see how accurate they are. Again, you can see some of the cycling voltage profiles that I have there on the right corner there. You can see how accurate the simulation predictions can be, and that is because we have this in-house capability to develop and optimize our models. So that takes me to the product simulation tools that we use here at UKBIC. We are quite fortunate that we have some of the best-in-class simulation to commercial tools that we've invested heavily on. And also, we also have the capability to build and develop our own tools. For example, the parameterization estimation tool that I talked about is our in-house tool, which uses a physics-based model that is fused with some machine learning models that we can accurately predict some of the hard to predict model parameters from the Newman model to all the way to other modeling techniques that we use, such as the molecular dynamics, the element model, and then even equivalent circuit model for module and pack. And that is coming towards the end of my presentation. But what I want to say before I hand over to Helen is that at UKBIC here, we develop a standard cell that we use to benchmark customers' products. And that was driven by simulation. As you can see here, we have our 21700 and the large power cell, which is driven by simulation. And you can see that even before these cells were built here, we've already predicted their performance. We already know what they are going to be, their behavior or the trends of the behavior. So we have this capability to be able to do this here at UKBIC. So in summary, for all I've said so far, we have the capability to develop highly accurate electrochemical model that are coupled with other physics. And this helps us to know before we build. We can do due diligence, not only on the design processes that we do here at UKBIC, but also on customer products. This helps us to reduce cost and again, fast track the cell manufacturing processes. So on that note, I'm going to hand over now to Helen, and she's going to take us through the process simulation. Thank you very much.
Thanks, Kenneth. So my name is Helen Walker. I am the process simulation engineer here at UKBIC. So my job is to produce simulations of the different manufacturing processes down the production line, to enable us to better understand those processes, but also to reduce, wasted time and materials on the line, so we get those process parameters right first time. Please excuse me for one moment. So at UKBIC, we use process simulation to model the processes that we have on our own production line. So most recently, we've been focusing on modelling of slot die coating. We've been modelling degassing and we've been modelling calendaring. We're also working on other models of drying, of mixing, and of web tension slot die coating. Although we have focused on modelling the processes that we have in-house, we are not limited to modelling those processes. So if a customer has, for example, a different method of coating, because we have the physics capability there, we can model processes that are above and beyond what we have at UKBIC. In battery manufacture, there are some quite weird and wonderful materials that you deal with. So being able to model the slurries that we deal with, we need the physics capability. We need to model multi-phase, non-Newtonian viscoelastic flow. We also can model linear and non-linear mechanics, and we can couple those two things together and produce fluid structure interaction models. And then if it's appropriate, we can also add an element of heat transfer into our models too. So at UKBIC, process simulation is very powerful because we have these 4 strands in one place. So I guess first off, the simulation engineers at UKBIC, we have experience in modelling the processes involved in battery manufacture and the nuances and the things that make it awkward. But to have an accurate simulation, you also need accurate inputs. And Kenneth has touched on this before. We have a fantastic laboratory that is able to characterise not only cells, but also the raw materials that we work with. And I'll talk a little bit about that in a second. The fact that our simulation engineers have access to the production line is also really powerful. We have real hands-on experience in the equipment, how it works. And if we have a query over a process, we can go down and verify what we're modelling is correct. And then finally, we have data scientists here at UKBIC, so we can perform advanced data analytics on production data. We can use that data to validate our models and also produce data-driven models as opposed to physics-based models. So I mentioned that our laboratory is fantastic for materials characterization, and we've spent a lot of time specifically related to slurries in developing our material characterization abilities. So we work really closely with some of our academic partners, and we've been working with the University of Birmingham through a Faraday Industrial Sprint to better characterize our slurries, which is really, really important for slot die coating. So we were awarded this rheology fellowship from the Faraday Institute, and it was looking at a multitude of things. We're looking at how formulation and scaling up from different size mixes affected rheology. But one of the really, really valuable things that we got out of it was how to characterize our slurries accurately. So we were looking at, firstly, how to use your rheometer and set up your rheometer such that you can really extend the shear rates that your rheometer can look at and get a really, really extended flow curve. We also looked at how to evaluate the contact angle that our slurries make with our foil substrates, and also how to get reliable surface tension measurements. So the postdoctoral researcher at Birmingham derived all of these best practices, and then we have adopted them at UKBIC, and we are now able to do all of that characterization in-house and really understand our slurries. And it provides a really nice input into some of the coating models. There was a publication that has come out of this work with Birmingham, and on the slide pack that will be released, there'll be a link to that. So process simulation is used throughout the lifetime of a campaign, and we like to get involved before a project kicks off. If there is a piece of modelling activity that's a bit unusual or a bit different to what we used to, we like to do an initial feasibility assessment before we can commit to that. The moment a project kicks off, we then start all that really good material characterization work to get those really accurate inputs into our models. And then the simulation engineers work really closely with the process engineers to inform the process parameters prior to production. After production, I mentioned we have our data scientists, and we can do advanced data analytics and lab work, and those two things together help us validate our models. And if there is any model refinement that is required, then we can go back and do the necessary model refinement, and then we will produce a modelling report. And if a customer is to then come back again in the future and reprocess that same material, we're in a really strong position because we have these validated models ready to go. So I've spoken a bit about coating simulation, and this has been the biggest area of development for us. So when we mix a slurry, an electrode slurry, and we go to coat it, if you haven't coated it before, it can be very tricky to anticipate the setup of the slot die coater and the process parameters that you need so that you get nice uniform coating, which ultimately will result in a better cell. And you don't want to waste time and material on the production line. We know battery materials are really expensive. So if we can predict in advance how to set up that slot die, we can save a lot of money and time on the line. So our solution to this was to produce a multi-phase CFD model of the slot die coating process, using all those material properties that we've spent a lot of time working on to predict, and in this instance, it's predict high edges. So there is a case study of this on our website to view later on. But yeah, what we're really trying to do is predict high edges during coating, because ultimately if your high edge is too large, you can't take that downstream to process it. And when we interrogate the model, we get cross-web thickness measurements, and you'll be able to see here just about for different scenarios. We're looking at trying to minimize that high edge, and that can be through the slot die design itself, the distance the slot die is from the foil. It could be the coating speed that you're looking at. It could be a number of things, and we can try different geometries and different process parameters to advise the process engineers of how to set up the process. So before we had this CFD tool, we could change our shim in the slot die up to 3 times during our campaign. And this can be really time consuming. Our slot dies at UKBIC are huge. You have to crane them off, clean them, change the internal shim, crane them back on. It's hours and hours during a campaign. We're at the point now where we can choose the slot die design right first time. So it saves a lot of time and energy on the line. You can imagine that when you're coating at 5 or 10 meters a minute and you're playing with process parameters, you can waste hundreds of meters of material doing that dialing in process. We've reduced the meterage of material significantly since we've implemented this modelling approach. And then there's also small other wins. So for every meter that you're not wasting dialing in, there's an energy associated with the drying. Our dryers are huge at UKBIC, and it's a significant energy saving that we're making. So coating is the big area that we spent a lot of time and energy on. Something that's been implemented recently at UKBIC is a degassing model. So whereas the coating model is this really high fidelity, complex multi-physics model with non-Newtonian flow, the degassing model is actually just a single equation that we're solving. And what we're trying to do is, following our intensive mixing process here at UKBIC, we have to degas our slurry under a vacuum. Now, if we don't get that right, you can end up with circular defects in your coating. So we have this one equation now that we solve, and it really helps us to inform how long we should leave our slurry to degas, so that we don't have these circular defects during coating. This is really nice, especially for people who run quite high fidelity, complex multi-physics models, because this model in particular has a runtime of about 30 seconds. So yeah, really nice to have a quick tool for a change. And then something that is coming up soon is a calendaring simulation. So when you are calendaring, there are a number of different defects that can be produced in both the coated part, but also in the current collector. And these are largely problematic for downstream processes at welding or other cell assembly processes. So we wanted a tool which would predict the onset of these defects. The solution that we found was a finite element mechanical model of the calendaring process. And so the basis of this model is the coated material is modelled as a crushable foam, and you need as the input to that model sort of the macro material properties, and you can gain them from micro indentation measurements, for example. And you model that as a crushable foam, and can we see the onset of defects in the coated part or in the foil? So I've got a small video here, and what you'll see is the foil is moving from bottom to top of the page, and you'll see the location of where the calendar rolls nip the material and where the defects start to be developed. So the calendars are nipping around about here, and you can see the onset of the wrinkling or the embossing of the foil. Now, I mentioned that some of the models that we work with here are quite high fidelity and quite complex. The particular challenge with this calendaring simulation is the scale of it. So it's a finite element model. It's got, I think it's about 700,000 elements, but we need high performance computing to solve this model. So we've recently invested in the ability to do cloud high performance computing at UKBIC. Yep, okay. So I guess in summary, the benefits of both product and process simulation at UKBIC, I mean, first and foremost, quite often it's time and cost reduction. So from a product point of view, we reduce those iterations in the design, make, test cycle. From a process simulation point of view, I'm really focused on reducing that dial-in time on the line. We're able to conduct due diligence on customer designs and check the feasibility of their claims. One of the most powerful things about simulation is not just understanding if something happens, but why. You can look at data and it'll tell you patterns in the data, but being able to simulate the physics, you can really dig into the models and interrogate exactly why things are happening. You're able to verify materials, equipment, and your designs in advance of time. And then finally, simulation can unlock rapid process and product optimization. There are, designs of experiments that are just not feasible to do when you're talking about using battery materials and manufacturing cells. But if you can do them in a simulated environment, you can, you're able to save a lot of money. So yeah, we're able to really, really unlock the power of virtual DOEs, parametric studies to facilitate these design changes and mitigate uncertainties. And I think that's all from me. So I'll pass back to Robert.
Thank you very much, Helen. Thank you very much, Kenneth. It's really appreciated. We are now getting to the end of the webinar itself. It's now time for questions and answers for those people that have some, and I see we have some already available. I'm not sure who will answer. However, first question from Faizan is, are COMSOL and ANSYS good pieces of software to carry out battery simulations? What's your take on these softwares? Thank you.
Thank you very much, Faizan. Yeah, I would say that they are really good tools. It depends on individual preference and the flexibility that you can achieve from both. But yes, they both have their advantages and not so, I wouldn't say disadvantages, but yes, I mean, the short answer to that is that they are really good tools that you can use to perform a battery simulation. We have both those here at UKBIC in addition to our own in-house developed tools. Yeah, thanks.
So the next question is from Kunal, and he has asked us, please elaborate on the multi-objective optimization algorithm. Do you use PSO/GA? If so, what is the usual population size and number of generations? Thank you.
Yeah, thank you, Kunal. Yes, at UKBIC here, most of the optimization algorithms, they are genetic based. So we use genetic algorithms and the particle swarm optimization algorithms. The number of the population size and the number of generation depends on the number of parameters that we are trying to identify or estimate. So it could range from a population size of 50 to 100, a number of generations from 20 to 100. So it depends really on the number of parameters that we are trying to estimate. But what is really key in our optimization process is that we always want to ensure that there is no elitism, and as well as ensure that the per generation tolerance is quite very low, as low as possible, to guarantee that there is no overfitting as well as eliminate elitism. Thank you very much.
Thank you, Kenneth. Next question is from Malif. If you can shed some more light on your parameter calibration for close match with experiment, and how do you do it? Thank you.
Okay, so one is that we have a well-defined or universally accepted battery simulation models. We know the parameters and we know the test conditions to achieve to identify these parameters. But what we do first is we receive or obtain some voltage profiles from few test conditions, and we try to fit this voltage profile in our simulation and parameter estimation process. And once we predicted those parameters, we do a full cell teardown and some of these tests in the lab and compare the the data, the value of the parameters we estimated by doing a purely experiment-based parameterization with the optimization-based parameterization, and then we compare the difference, and that helps us to tune the parameter, and then we predict some unseen test conditions, so that when you now bring the data of this unseen test condition, you see how accurate that the prediction becomes. So this is the process we use to tune or to do parameter optimization or identification. Thank you.
Thank you, Kenneth. Another one from Malav. Here we have what mechanical properties of crushable foam you need in calendaring simulation?
Yep, so I can answer that one. So yeah, it's a stress strain curve that you need. I think it's a principal stress versus volumetric strain. These are quite tricky to get because if you don't get when you're doing the indentation measurements, if you don't get the size of the indentation tip correct, you can get really, really noisy data. So we started with nano indentation measurements, and that was not successful. And so now we use micro indentation measurements. So yeah, you really need to make sure that your punch head is big enough relative to the particle size in your coating material. Yeah, so not easy to get these material inputs for the calendaring model.
Thank you, Helen. And the next one is from Josin. What information does surface tension give you regarding processing?
So in the multi-phase models, in the CFD models for coating, surface tension is required. The models aren't very sensitive to surface tension. So you can conduct sensitivity studies, for example, for the coating model to contact angle and surface tension. And surface tension will impact the size of the high edge that you get, but it's quite slight. Whereas contact angle makes a significant difference. And so we've had customer campaigns where, by way of the formulation of the slurry and the substrate that they're coating on, high edges have almost become, I'm going to say, unavoidable. However, we have been exploring corona treatment at UKBIC, and so actually that hopefully contact angle won't be such a problem in the future because we can modify the surface energy of our foils.
Thank you, Helen. That's really good. And question here from Carlos. What is the biggest limitation of current state-of-the-art simulation technologies for battery physics-based modeling?
I think from my point of view, that would be the simulation speed, because we now in battery simulation, we rely on the DFN model or the single particle model to be able to speed up. But if you really want to get a deeper insight into the processes that goes on inside for lithium-ion battery, for example, you need a detailed microstructure mesoscale model. But again, you can't really simulate that with the current existing commercial tools because they are quite computationally expensive. So that is what I think is the limitation. Again, in parameter optimization, some of the tools that you have can be able to do that, but they are not currently designed to handle some of the complexities that lithium-ion battery models has. So that's my answer to that.
I'll jump in on that too. In particular, from a coating and calendaring model perspective, it's the difference in order of magnitude in your dimensions. So within coating, our coatings are perhaps 100 microns thick, but we're coating maybe 300 or even 700 mil wide. How do you mesh something with those different length scales in is really, really tough. Now, luckily for coating, I can exploit the symmetry. It's one thing I can do. But we're still talking 8-9 million elements exploiting that symmetry for our half width coating. So it's really tough. It's computational expense.
Thank you both. That was really helpful, I'm sure. Another question, a couple of questions from Malav. What parameters do you fit usually? E.g. for ECM, is it RC? For welding tab ohmic resistance?
Thanks, Malav. Yes, that's correct. For equivalent circuit models, we usually fit the RC network. And again, the ohmic resistance, the sort of parameters that you see in your ECM models. Again, some of our ECM models includes, or we have degradation parameters, degradation mechanics included in them, so that we can be able to predict how these parameters changes with aging of the cell. So we also tend to predict these parameters usually at the beginning of life, and then compare that with cycle cell data and compare the performance for subsequent parameter tuning. Thank you.
So the next part from that from Malav is, what kind of SS curve is that? Uniaxial, biaxial, shear, or compression for countering? Who's the
Yes, that's for me. Yeah, so it is uniaxial compression. How well that reflects a rolling process, you could argue. Yeah, you could argue that there's some debate over whether that's truly reflective of the rolling process. But yeah, it is a uniaxial compression curve from the indentation measurements.
Thank you, Helen. Brindley Smith, have you been using the slot die simulation to predict operating windows for coating of a slot, including air entrapment, etc., of particular rheology? Properties, sorry, missed the rest of that, as well as cross-web uniformity. If so, how accurate have you found this prediction to be?
Yeah, so the majority of the slot die coating simulations that we do are they are steady simulations. So we don't explicitly model the air entrainment. However, we can interrogate the model and we can see where the meniscus under the slot die lies. And we know that if that meniscus is, let's say, sat very close to the slot die exit, we're at risk of air entrainment. If our meniscus is really nicely pinned at the upper slot die lip, then we are confident that that setup wouldn't risk air entrainment. Let me just read the last bit of that question. And then, so asking how accurate simulations are. In the case study that is referenced online, there are results of the simulation overlaid with line side measurements. So you can see how nicely the simulation is able to predict the high edges. So we do find it to be very accurate. Have a look at the case study.
Thank you, Brindley. We have a question from Sanglam. Is the surface tension assumed to be constant value for coating simulation?
Yes, it is. Yes. And sometimes people follow that question with, is your contact angle a dynamic contact angle or not? And we just use a single value for our contact angle. Yep.
I have a question here from Andreas. It says, what is your take on physics-informed machine learning models for process simulation, i.e. few physics-based simulations to then to train an ML model?
Okay, so on this point, we have now run our coating model a significant number of times on quite a few different slurries with different contact angles and process parameters. So we do have a database of results from the coating process simulation, and our data scientist is now interrogating it to try and reveal trends. At the moment, the focus is, what is the relationship between the flow curve versus the prevalence of high edges. However, we need to generate more data. We're at about 100 different coating runs at the moment. And the data scientist in my team is coming back and saying, you've got gaps, can you run some more cases? Because I'm not confident that the model is able to interpolate in this region. So machine learning models based on physics, process simulations are coming. And again, I mentioned because of the runtime of simulations, it was largely driven to tackle that problem. To speed up model turnover. So we have not been able to validate the location of the meniscus. We just don't have the camera setup or the imaging in place, under our dye lips. What I mentioned that we work with Birmingham University earlier. It's a capability that I understand that they do have. So they are able to visualize and see the location of the meniscus on their roll-to-roll slot decoder. So it would be a nice bit of research to do. But yeah, I've not been able to validate the model on those specific grounds.
Hopefully that answered your question well, and there are no further questions in the chat. So I think, again, thank you to Helen, thank you to Kenneth for the valuable support to people. If you do have questions, refer you back to the slides that will be available. Thank you for turning up. Thank you for listening. We appreciate it here at UKBIC. We're here to help people. We're here to promote what we do and help everybody be better at what they do. So feel free to reach out if you need some help. If you want direct contact, we can arrange that as well. Thank you ever so much for attending. Thanks very much.